Today is a very exciting lesson because what we are actually going to do today is figure out what that anti-differentiation or that integral equation is. So it's like we know f prime, but how do I get to f? So it's super important to note, just some vocab and definitions, that the process of finding an antiderivative is anti-differentiation. So if you hear that, you know all that means is we are finding the antiderivative or we're integrating. The family of all antiderivatives is known as the indefinite integral. We've talked about definite, and in the days to come, you're going to see us move back and forth between these definitions. And it's super important to note that the only difference between like definite and indefinite is sometimes we don't have all the information. We'll talk about this more. But it is important to note that this indefinite comes from this idea of adding this plus c, or this constant of integration. Again, we're going to revisit this. No worries now. These are just important things to get written down so that when they are mentioned later, you know what we're talking about. Notation for antiderivatives. When we are looking at antiderivatives, you may see dy over dx, f of x, or sometimes that dx is multiplied and you're given dy equals fx dx. So general antiderivative notation, when we're looking at this guy, we have our variable of integration, this dx. This fx is the integrand. Yesterday, or I guess not yesterday, on Thursday we talked about this, and this is also known as the derivative. And then we have our antiderivative. And then this plus c is our constant of integration. This plus c is going to be very important, and again, we'll look at it in a second, and you'll get a really good idea of what it means. A super important conclusion is that it is important to know that if the notation is a lowercase f of x, if that integrand is lowercase, then that antiderivative is that uppercase f of x. In other words, f prime of x is equal to f of x. However, if we're given an f prime of x in that integral, then when we antidifferentiate, then that is a lowercase f of x. So it doesn't jump straight to that uppercase. The kind of like the order is like f prime of x, f of x, capital F of x. So that's kind of an important thing to note, that if you see it jump from capital F to f prime, that's two derivatives and not just one. Now, for indefinite integrals, what the whole process is that we are given a derivative. Like we know dy over dx is f of x. Once I multiply by dx, I get dy equals fx dx, and then I anti-differentiate. So I have y equals something times f of x dx, because that is that derivative function, and I'm left with that capital F of x. Some integration rules are that the integral of 0 is c, and it's really important to remember that integration and derivatives work backwards. So for example, if I had, let's say, 2x squared plus 3x, right? So let's call this f of x. And I would get f lowercase f of x equals, because I'm saying f prime of x equals f of x, we would have 4x plus 3. So we have gotten really good about going this direction, but today we're going to go that opposite direction. So it is super important to note that when I am working backwards, some of these rules, and we're specifically going to look at this guy today, that if we have the integral from something times x to the something minus 1, when I integrate that, I get x to the n plus c. Now, what we're going to start thinking of is like, okay, how would I get this for x? I would be like, okay, I multiplied something. I would be moving this up 1 power, right? Because this is x to the 1, but I know if I integrate, it would be x squared. And then you would say, okay, so this would be x squared. And then I also know that this 2 got multiplied by some coefficient in order to lend that 4. And I know that 2 times 2 is 4. This is x to the 0 technically, right? But if we're working backwards, x to the 0 becomes x to the 1. So I know that that has to be 3x. We'll establish a rule in a second. But let's kind of start doing a few examples here. And I want for you guys to maybe bear with me for this first one and then take a pause. If your derivative is -2, I'm thinking, okay, what did I differentiate to get -2? You would say, okay, -2x. But because when I take the derivative of a constant, that derivative is 0, that's where this plus c comes in. Because I don't know if there was something that I took the derivative of that disappeared. For example, like let's go back to this previous example. Let's say that f of x was 2x squared plus 3x plus 4. This 4 is important, right? It has an impact on our function, but I would only get the derivative to be 4x plus 3. That 4, that constant, would disappear. So what we're saying is that when I'm working backwards, I have no idea if there is a constant. So I leave a c in its place because I'm saying like, okay, this could be, there could be a number here, or that c value could be 0. I don't know without more information. The integral 17, we're saying like, okay, what did I take the derivative of to get 17? I know that this is technically x to the 0, so when I raise that up by a degree, I would get 17x. And I know that if I differentiated, the nicest thing about integrals is you can always check super fast, that I would get this guy right here. However, I don't know if there was a constant that disappeared, so that plus c comes into play. All right, let's look at something a little bit crazier. I don't know what's going on here. 7x to the 6th. Okay, I'm saying like, how did I get 7x to the 6th? What did I differentiate to get there? I know that I have to move up a degree, so that started off as x to the 7th. I also know that when I differentiate, your exponent becomes your coefficient. So 7 times 1 gives us 7, which means that that coefficient would be 1. I don't know if there's a constant, so there's that plus c. Really nice thing about this guy, number 4, this would just be 5 f of x, right? Because the derivative of f of x is f prime. And then also, again, don't know if there's a constant, plus c. I want for you guys to take a second. We're going to establish rules in a moment. So for those of you who like, I need a rule, then don't worry, we'll catch you. But if you are someone who is like, okay, this is interesting, it's a good puzzle, take a pause here and try to do 5, 6, and 7 on your own, and then play and check your work. All right, we should have something that looks like this. I split up this guy using my rules, right? My integral rules, we looked at that yesterday. I said that this is the same as we have the integral of 3x squared, the integral of 17. Technically, both of those would have a c, but because I don't know what each of those constants are, then you can lump your c's together and just have 1 plus c. From all of this information, we establish our power rule. So here's where, those of you who love the rules, here it is for you. The rule for integrating x to the n d of x is that we have x to the n plus 1, right? Because integrating is the opposite of differentiating. So instead of losing a degree, we're gaining a degree. And then this is going to be divided by that n plus 1. Make sure you have plus c. This plus c is very important. And this is as long as n does not equal -1, right? Because that -1 plus 1 would get us to nothing. So let's look at some examples. We have all these rules. These are in your notes. Write them down a later time. But note that all these rules, here's what we're going to mainly be working with today, this general power rule. And for trigonometry, it's going to be very similar to if you memorized all your derivatives, your integrals are easy. You just work backwards, right? So if the derivative of sine is cosine, the integral of cosine is sine. If the derivative of cosine is negative sine, the integral of sine is negative cosine, right? Very similar. We also have some special rules for special functions. E to the x, remember, always fickle, doesn't really change. We still have that plus c. If we have an a to the power of x, you know that derivative is a to the power x with a natural log. So that integral, that natural log goes to the denominator. And then with natural log of x, we would have 1 over x. So when we have that integral of 1 over x, we get natural log of the absolute value of x. We'll talk a little bit more about this as we go. The whole idea of this absolute value sign is to keep the domain the same from that 1 over x, but we'll get there. We'll get there as we go. So now that we've established this power rule, I'm going to take us through some guided practice to show you guys how to use this. So if we have x to the 7th, we're saying, all right, 7 is my in value. So if I am anti-differentiating or integrating, we would have x to the 7 plus 1 all over, my in is 7, 7 plus 1 plus c, which gives us 1 over 8, x to the 8th plus c. Remember, you can always double check, right? So like we're saying, okay, let's differentiate this guy. 8 times 1/8 is 1. Then derivative of constant is 0. Take that down. So x to the 7th, good to go. If I have an x to the negative 3, now my in is negative 3. We are saying this is x to the negative 3 plus 1 over negative 3 plus 1. Plus c. Whew, almost forgot that for a second. Once I get that done, you should have x to the negative 2. Because that's a negative exponent, I'm going to throw that in the denominator. And that coefficient is negative 1/2 x squared. And then we have that plus c. Any version of this would have worked. This was just my most simplified version. All right, for 7x squared, we're going to go to that rule that says that constant can come outside of that integral. So I'm going to say this is the same thing as 7 times the integral of x squared. And once again, my in value is 2. So we have 7 times x to the 2 plus 1, which is cubed, all over 2 plus 1, which is 3, plus c, which gives us 7/3 x cubed plus c. If you are like, okay, I'm starting to get the hang of it, I would encourage you, once again, the more you practice this on your own and then like either get it correct or fail gracefully, right, the better you become. So I would encourage you to press pause and maybe try some of these others on your own. If you are like, whoa, I am not there yet, then stay with me. And we're going to keep on going through. I know this next guy right here I'm going to rewrite. This is going to be the integral of x to the 1/5. So when I integrate this guy, we're doing 1/5 plus 1, so we have x to the 6/5 divided by that 1/5 plus 1, which is still going to be 6/5. Remember, when you divide by a fraction, you flip and multiply. So we're left with 5/6 x to the 6/5 plus c. Just following that rule. For x, 1 over x to the 5, I'm going to rewrite this as x to the negative 5. So again, when I integrate, I'm going to add 1. So I have x to the negative 4. This is all over negative 4 plus c. I'm going to rewrite this guy as negative 1 over 4x to the 4th plus c, just to keep all my exponents positive. For number 6, I would simplify this first. You guys will go through more of these rules and ideas later, but let's get this simplified. We have x to the 4th minus 3x d of x. Remember, once again, this like breaks up, right? So we take the integral of both that x to the 4th and that negative 3x. So that in value for my first term is 4. So we have x to the 5th over 5. For my second term, that negative 3 gets factored out. If my in value is 1, so we have x squared divided by 2 plus c. And you can leave it like that, or you can rewrite it as 1/5 x to the 5th minus 3/2 x squared plus c. That might feel a little bit more traditional. And again, remember, you can always check by taking the derivative and ensuring that you get back to that original form. For 1/7x cubed, again, let's rewrite this guy. I'm going to write this as 1/7 times the integral of x to the -3. I think this is kind of important because I don't want to have to deal with that 1/7, right? That is a coefficient. When I integrate this, my n is -3. So that k value is 1/7. We have x to the -2 divided by -2 plus c. Remember that plus c, be important. So when I get this done, you know that this is going to be 1/-14. I'm going to move that x to the -2 to the denominator plus c. I want to take a moment very quickly to go to this idea of what this plus c means, just to stamp this. This whole idea of this plus c, if I'm looking for a function whose derivative is 3x squared, all of these functions, these are all cubic, right? These are all have a derivative of 3x squared. So let's use those rules. If I'm integrating 3x squared, I would get 3 times, right, x plus 1, so that's x cubed, divided by 3, which is x cubed. The reason this plus c is important is because any single one of these, so let's say that f1 is x cubed plus 5, right? So let's say that this guy, I'm going to get a highlighter here. Let's say that this guy is my f1, x cubed plus 5. Let's say that this guy is x cubed plus 3. Let's say that this guy is just plain x cubed. So I'm going to write these down. X cubed plus 5, x cubed plus 3. Just plain x cubed, right? We could even move on, right? X cubed minus 2.8, x cubed minus 5. All of these guys have the same derivative, which would be 3x squared, even though none of them are the same function. So that whole idea of that plus c is that, like, we don't know. We don't know what that constant is, or if there even is a constant. So that's why that plus c is so important, because we have to allow for the benefit of the doubt that I don't know what this value is without having more information about the function. This is all I have for today. I would encourage you to click on that Khan Academy link and practice some of this. Also, if you're feeling like, ooh, maybe I want to go a little bit deeper, we're going to continue these practices, but I would encourage you to maybe check out these examples and use your rules. I'm going to post the answer key in a second, but if you are like feeling very overwhelmed with what we just did, stop there and practice, and we'll come back to these guys later. And here is that answer key here for all of my overachievers with those special conditions. So we have my, you have some cosine going on here, some expanding or some foiling, some simplifying and then integrating, and then some more simplifying, expanding first, simplifying, and then integrating. So these are all some tricks just to kind of keep in mind, and it's okay if we're not perfect yet. We just have to have some idea of maybe these are some ways that we can get those answers.